Hi everyone, my name is Thijs, I'm the technical evangelist at Varnish Software, and today I'll show you what an S3 shield is and why you should consider shielding your S3 buckets with Varnish Enterprise. S3 itself needs very little introduction. It is short for Simple Storage Service, and it's an Amazon Web Service that is the de facto standard for object storage in the cloud. Not just the S3 product itself, but the protocol and the API it offers are in the industry standard and are widely adopted by other storage vendors. S3 is known for its scalability, its global availability, its ease of use, and its flexible pay-as-you-grow payment model. So why would you need to shield an S3 bucket? Well, the answer to that is performance and network latency and cost. So despite the seemingly infinite scale of the cloud, S3 doesn't focus on pure performance. It's not a guarantee. Instead, it prioritizes its scale and its resilience over that performance and network latency. And of course, there's also a cost associated with using S3. There is a consumption cost and a storage cost. And you've probably heard of cloud egress charges. They're a very hot topic these days. Well, these also apply to S3. So the more data you pull from an S3 bucket, the more it could potentially cost you. But before we talk about any of that, let's focus back on performance and on network latency. And I'll do that with the following diagram. The locality of an S3 bucket really matters. The closer you can put it to where it's consumed, the faster it will go. And as you can see, we've deployed an Amazon S3 bucket in the US East 1 region. There's also 2 EC2 nodes in there. Those will be fast, of course, because they're hosted really close to the S3 bucket. But as soon as you go beyond that, for example, we also have 2 EC2 instances hosted in the AWS US West 2 region. Well, there's no guarantee for performance there. And all performance guarantees go out the window as soon as you leave the cloud. In this case, we have a Google Cloud Platform zone in US West 1, where we have 2 GCE instances. While there is no performance guarantees for those, neither are there performance guarantees or latency guarantees for those 2 bare metal instances that we host outside of the cloud on-premise in Dallas. Despite the dominance of Amazon in the cloud market, they are not the only game in town. So yes, S3 is the industry standard, but other cloud vendors are out there as well. And the diagram and the example I showed you talked about a hybrid or multi-cloud approach. And in this case, even combined with on-premise hardware. And while performance is a factor, it's the cost aspect that is really on people's minds. There is a storage cost associated with S3, but that's not relevant for this video because an S3 shield is not going to alleviate that. But it's the consumption cost. It's the cost of the API calls being sent to S3. And of course, the data transfer costs, the egress charges, as we call them. So let's revisit the example and that diagram and approach it from a cost perspective. The focal point of this example and the diagram is the S3 bucket that is hosted in the US East 1 region. Data transfer between that S3 bucket and the EC2 instances in that same region are free of charge. That means those EC2 instances will not incur any transfer fees. There are no cloud egress charges. Everything stays within that same region. However, when we start consuming that S3 bucket and taking objects from it from EC2 instances in the US West 2 region, there is a cost associated with that. And that starts at 2 cents per gigabyte. Of course, it's tiered and you'll find the pricing online, but it is not free of charge. And it becomes more expensive when we go outside of the Amazon cloud. If we try to fetch content from the S3 bucket from the Google Cloud or the on-premise servers, it starts at 9 cents per gigabyte. So how does an S3 shield work? How does it alleviate pressure from those S3 buckets? And how does it improve performance, reduce network latency, and reduce cost? The idea is that the S3 shield, powered by Varnish Enterprise, caches frequently accessed objects from an S3 bucket and stores those in a cache positioned close to the consuming client. This means that the S3 bucket is less frequently accessed. Again, the copy that they need is readily available a lot closer to the user. This guarantees performance and low network latency, but because of the infrequent access that is now taking place to the S3 bucket, your AWS bill decreases as well. So let's approach that idea and apply it again to our example. So let's draw again the diagram and talk about cost reduction. As you can see in the diagram, the Varnish-powered S3 shield will store copies of popular S3 objects on a server in the AWS US West 2 data center, in the Google Cloud, and on the on-premise environment. And at first it looks like simple content duplication, where content is stored in the different regions. It seems to add complexity and might be hard to manage, but that's definitely not the case, because Varnish is a reverse caching proxy. It only stores the S3 objects in the cache for a limited amount of time. And it also knows how to revalidate the content and where to fetch updates from. So fetching uncached S3 objects and revalidating expired objects will still require data transfer to some extent. But retrieving cached versions of these objects will require zero interaction with the S3 bucket and will also significantly reduce your AWS bill. So now that you know how an S3 shield could reduce cost, it isn't a big stretch and it doesn't require a lot of imagination to understand how it will reduce latency and increase performance. So again, the same example, the same diagram, but approaching it from a performance point of view. Yes, we have those caches in those same regions, in the Google data center, in the AWS US West 2 data center, and on-premise. Yes, we store frequently accessed S3 objects there, and we reduce the access to the actual S3 bucket. And for the duration of the cache that is predefined, the objects will live there and will perform really fast because the proximity between the consuming server or the client and those cached S3 objects is minimal. Please bear in mind that there's still an interconnection required between the S3 bucket and the S3 shield. So network latency might still occur when cache misses occur, or when revalidation has to take place. But as soon as the S3 objects are stored in the cache, they will perform really fast and they're no longer dependent on that interconnection between the Amazon cloud and your S3 shields. What makes Varnish Enterprise such a good candidate for an S3 shield? Well, Varnish is a very powerful, very flexible and lightweight reverse caching proxy. It stores content that originates somewhere else, it stores it in the cache, and serves it to requesting clients upon subsequent requests. It respects HTTP's built-in caching mechanisms and allows for far-reaching customizations of the caching policies thanks to its built-in programming language called Varnish Configuration Language. Varnish Enterprise is the commercial version of Varnish and has a lot of extra features and a lot of extra capabilities. One of those features is a dedicated S3 module that allows easy access between Varnish and an S3 bucket. It also has a set of AWS-specific VCL scripts that tackles the connection, but also the authentication using the authentication protocol that is very specific to S3 buckets. So yes, from a feature perspective, it is an excellent match. But what makes Varnish itself so powerful, and won't it become a bottleneck itself? Well, the answer is obviously no. Varnish is built for performance and built for scale. It uses very little server resources and has as few operational and functional responsibilities as possible. That allows it to take on a lot more requests and allow a bigger concurrency. So what's the secret, you may ask? Well, there's no real secret. There's just a set of architectural decisions that make it so powerful. Here's what we do. We make efficient use of the available memory. We're not CPU bound at all. We hardly access the disk at all, knowing that it's the slowest part of the system. We have a very powerful threading model, and we apply specific kernel features and system calls to have a limited footprint on the server. We now covered the basics and you know what an S3 shield is, what type of issues it solves, and why Varnish Enterprise is an excellent candidate. You probably want to get started now, and we provide some online resources to facilitate the process. Starting off with a collection of automation recipes made available on our Toolbox repository. Just go to github.com/toolbox and navigate to the S3 Shield folder where you will find the different recipes ranging from Ansible playbooks, Terraform automation, cloud-init scripts, Docker Compose orchestration files, and Helm chart orchestration. We also have a dedicated tutorial on our developer portal regarding these automations. Go to varnish-software.com/developers, go to tutorials, and navigate to the S3 Shield tutorial. You'll find it all there. Let's start off with the requirements. The first thing you need is, obviously, an S3 bucket. That's what we're shielding. It's either an official one hosted on the Amazon cloud or a competing object storage product that has a compatible interface. We need the full address of the bucket along with an access key and a private key to privately access that content from the S3 shield. All that information is stored in an s3.conf configuration file. It's used by all the automation recipes and also has an additional parameter called s3ttl that states how long the S3 shields can cache the objects prior to revalidation. This defaults at 100 seconds. Another requirement is a VCL file with the customized code in it that uses the S3 module. We have that readily available on our Toolbox repository in the S3 Shield folder, and that will be orchestrated by all the automation recipes. It's easy, it's just drag and drop. And of course, another requirement is having access to machines on which you can install Varnish Enterprise. That either happens using some of the automation recipes that require a license key, which you need to purchase from us, or if you're using one of the marketplaces in the cloud, that is handled there. So let's start with the first one, which is orchestration using Ansible. In order to have the automation recipes available locally, including the Ansible playbook, you need to clone the GitHub repository. So open up a terminal, go to the folder where you want to check that out, and run git clone github.com/varnish/toolbox. Just navigate to the Ansible folder and you'll find it all there. Now you need some sort of an editor or an IDE to open up those automation recipes. I'm using Visual Studio Code, as you can see, and I've navigated to the Ansible folder. And the first thing I'm trying to open is the s3.conf file. You see it has a bucket address parameter and the templated value needs to be changed. I'm using Varnish example, which is hosted in the US East 1 region. We're also altering the access key and the secret key. I'm not going to add any real values there because this is sensitive data. Another interesting fact is that this Varnish example bucket hosted in US East 1 is actually a real one. And as you can see, it has a logo.jpg file that we'll access throughout the demos. It's a pretty big file, it's 4 megabytes in size, and it's an excellent one to test latency. Because I happen to be based in Belgium, the S3 bucket is based in US East 1, which is North Virginia in the United States. So there is a little bit of distance between me and the bucket, and that's excellent to show what the latency is about and how we can tackle that with an S3 shield. Let's continue with the Ansible automation, and let's go to the inventory YAML file that contains variables and hosts. The variable that we want to uncomment and change is the repository token variable containing the token that gives you access to the package repository. This is part of your subscription, you get that from us. Of course, these packages need to be installed on a set of servers, while in our case, in this demo, it's just one. Here's the IP address that Ansible will use, but because that server doesn't have a typical root username to access it over SSH, we provide an additional parameter called Ansible SSH user, and we set that to Ubuntu so that Ansible can log in using that username and, of course, the keys that I have stored locally to start instrumenting the automation. Once you have the s3.conf file in place, once the inventory.yaml file is completely customized with your repository token and the IP addresses of the servers on which we want to deploy the S3 shield, you can finally run the Ansible playbook command. Go to the command line, go to that very folder, the Ansible folder, and run the Ansible-playbook command with the -i parameter pointing to your inventory file so we know where to deploy to and what keys to use, and playbook.yaml as the playbook file to know what exactly we want to do. When you execute the command, it might take a little bit of time. It runs all the commands, deploys all the files, does all the customizations. And in the end, you will see that the Ansible orchestration is done and that on server 83, 217, 69, 173, you have a fully deployed S3 shield. Want to see what that looks like? Let's take a look. I'll run my tests mostly using curl. Curl is a command line HTTP client that we can use to get the right information out of. The information I particularly care about is not the output. We know it's binary content, it's a 4 megabyte image, but we want the loading times, and we can get those out of curl by using the -w option and using the time_total parameter. So let's see what that looks like in terms of results. The first time we run it, it takes 258 milliseconds. We run it again, 240 milliseconds. And then of course we'll run it a third time, maybe even a fourth time, 231 milliseconds. Let's run it one more time, 315 milliseconds. Of course that's less than a second, but in terms of latency and total loading time, we could do a lot better. Remember, this is a transatlantic connection. I'm based in Belgium. This S3 bucket is hosted in North Virginia, hence the long loading times. Of course, when we retrieve that same logo.jpg file from the S3 shield, the performance should be better and the latency should be lower. So let's go back to the command line and you now see a split screen. On the left-hand side, you still see the curl command that points to our S3 bucket hosted on Amazon and the time total parameter that we want to display. On the right-hand side, we have an SSH shell on the server that hosts the S3 shield. We're running the varnish log command to get some log information out of there. We want a request URL and some timing information specifically for requests going to logo.jpg. But instead of sending your request to the S3 bucket, we need to enter the IP address of the S3 shield server and run it. And as you'll see, it took initially longer, 0.4 seconds, so 400 milliseconds. And that's because the fetching itself from the S3 bucket took quite a bit of time. But now it's stored in the cache, so when we run it again, the results are far better. We're doing this at 38 milliseconds, so that's 10 times faster. So we no longer need to fetch it because the response could be loaded in 25 milliseconds. And then of course there's a little bit of network latency in between where that server is hosted and where I'm located at home. That was pretty good, right? Performance was great, latency reduction was obvious, very easy to get started. Overall, Ansible is a very well adopted infrastructure as code tool, allowing you to provision any type of commercial off-the-shelf hardware, any type of virtualization, or even in the cloud. Everything uses SSH, packages are installed, but if you're focusing on the cloud, there is also another way. You can use our cloud-init script, so let's have a look at that. So we're going back to GitHub, to our toolbox repository, go back to the S3 Shield folder, and then try cloud-init. And just like any other of those automation recipes, again, there is an s3.conf file. That takes the address of our S3 bucket. In this case, we're changing it to Varnish example, hosting this in US East 1, and the access key and the secret key. You know the drill by now. There's also a cloud-init S3 Shield YAML template file that we will parse some information in. It contains the packages we want to install, files we want to write, using variables we want to replace and inject, and of course a token to install Varnish if required. We provide some systemd overrides, some other commands that we run, and using the generate YAML file, we will inject the values or base64 values of the default VCL, the S3 conf, and potentially the package token to install Varnish. We'll do a find and replace using the set command, use the template as the basis, and the output is the cloud-init s3 shield.yaml file. This YAML file contains the actual parsed cloud-init script that we can use to provision systems. Let's go back to the command line. We're still in the S3 Shield Git repository. We go to the cloud-init folder, and when we list the files, you see the files that we covered there. The s3.conf file, which contains all the information we need, the template that will be parsed, and also eventually the generate.yaml file. So now let's generate that file and use a token, and the actual parsed s3 shield.yaml file is there, containing all the base64 encoded values from the s3.conf, also including the VCL file, which is base64 encoded, and that will be used along with the token to install Varnish. We now generated a complete cloud-init YAML file that we can use on any supported platform. And yes, you have the usual suspects such as AWS, Azure, Google, and Oracle, but there's so much more. And when we go to the cloud-init documentation, you see a whole list of supported platforms. This list is definitely not complete. I'm going to try out Equinix Metal, which is Equinix's single-tenant dedicated hardware platform. It's a cloud platform that spins up bare metal machines, and it happens to support cloud-init. So let's do it. This is the Equinix Metal console. We're going to deploy a bare metal server on demand. We're going to choose a location where we're going to do that. I'm going to pick Amsterdam because it's closer. We're going to pick the smallest server. We need an operating system. There's a whole range of them. I'm going to go for Ubuntu. And then with the optional settings, there is a user data field. And there I can paste the generated YAML file. You can see that all the information is there, including the base64 encoded s3.conf. I press deploy, and now it's the waiting game. After a while, this server will be ready, and we'll use cloud-init to fully orchestrate the installation of Varnish Enterprise and all the specific S3 Shield configurations. The server setup is done, the machine is ready, and I can copy its IP address, open up a second tab, and try to navigate to the logo.jpg file. If that logo loads, it means the S3 Shield is successful. And as you can see, it is the case. We have a 4 megabyte image that is now stored in a cache, and that is offloaded from the actual S3 bucket hosted on Amazon. While the web browser example is great, you get to see something, we don't know about the exact latency. To know about the latency, we need to go back to the command line, use curl again, and use that -w parameter to show the total time. So let's get back. You can see that the old command is still hosted there, pointing to logo.jpg. And yes, it takes 248 milliseconds, 289 on the second attempt. So let's replace that S3 bucket address with the IP address of the S3 Shield. Now it takes long the first time, 370 milliseconds, but the second time it drops. And after a couple of attempts, we're down to 46 milliseconds on something that is hosted in Amsterdam. So again, pretty great. This procedure is great if you're running cloud-init on systems that don't have Varnish Enterprise installed. That's why we provide the token as an argument to actually have access to the package repository and install Varnish Enterprise prior to customizing the behavior. we can run the same generate.yaml script without a token argument. This will create a similar s3 shield.yaml cloud-init file, and when we look at the content, the token variable is now empty. And because of that, it will not install Varnish Enterprise using that install procedure. We assume Varnish Enterprise is already there because you're running this on a system that already has Varnish Enterprise installed, such as AWS, Azure, Google Cloud, Oracle Cloud Infrastructure, pretty much one of the places where we have a marketplace where we can monetize the use of Varnish Enterprise. This also means you don't have to pay the license up front. You can do it in a pay-as-you-go/pay-as-you-grow model, which is quite flexible. Let's run this cloud-init script on one of those platforms. Let's take Amazon, for example. Let me take you to the graphical user interface of the AWS console, where we're going to deploy an EC2 instance. You'll notice it's hosted in Paris, so definitely not the region where the S3 bucket is hosted. We can launch an instance. We'll call that one S3 Shield. And then, of course, we need to pick an image, an AMI. We'll browse through the AMIs. We won't take a common one, but we'll go to the marketplace. We'll type Varnish to find the corresponding images, and the first result is Varnish Enterprise 6, the official image that we offer, with free trial capabilities and an hourly license fee. You click Select, and you can read through all the information, but the important part is that you click Subscribe Now. You can run this on different instances, but we'll stick with M5 large. We'll select the TACE SSH key so I can access it using my own SSH key, and then from a security group point of view, everything is provisioned. The only thing that is left to do is go to Advanced Details, scroll all the way down, and go to the user data field where we can paste the cloud-init script. As you can see, the cloud-init script doesn't have a token, so it won't install Varnish Enterprise because we assume Varnish Enterprise will already be installed. We click Launch Instance, and now it will take a little bit of time before the instance is completely launched. We can go back to the overview. It says it's already running, but of course there is some initialization to be done, and cloud-init needs to be executed. That could take a minute or two. When we go to the S3 Shield details, you'll notice that the IP address is already there, so we're going to put that in our clipboard, and that will allow us to access the S3 Shield. I can use that IP address and run a curl command for the logo.jpg file, figure out the latency, you know the drill by now, but before we get into that, I want to access that very server over its IP address using SSH and see what actually happened using the cloud-init file. So on the command line, I do an SSH shell on Ubuntu at the IP address, and it takes me on the shell. I can then go to etc varnish, which is the folder where everything is installed, and you can see the VCL files, and you can see the s3conf, the s3 shield VCL file. There is also a systemd override for the runtime parameters. So if you go to the right path and go to the override conf file, you can see that we did an override on the -f parameter where the default VCL file is, and it points to etc varnish s3 shield.vcl. That was a quick glimpse under the hood, showing you how the automation actually takes place, but let's go back to our familiar curl command and see the latency. Running the S3 bucket again gives us a 414 millisecond total loading time. Replacing the URL with the address of the S3 Shield on Amazon, it gives us a similar total loading time. Of course, this is the first request. When the cache hit starts taking place, it is a lot faster at 69 milliseconds. Run it again, 73, 80, 68, 72, so it varies around that. Again, very decent performance. The install procedure on Amazon you just witnessed uses cloud-init to automate the provisioning, and yet the setup of the instance itself is still done manually using the graphical user interface. And while the AWS command line interface can be used to automatically spin up instances, I'd like to introduce another piece of infrastructure as code to take it to the next level. That is our Terraform scripts that are also hosted in the S3 Shield folder on the toolbox repository. Going back to my Visual Studio Code editor, you can see all the automation recipes. We already covered Ansible, we already covered cloud-init. The Terraform part, when we collapse that folder, has a bunch of TF files in it, which is short for Terraform. Let's start with the provider.tf that contains the API and provider information, as well as a region variable that says in which region we're going to deploy. There's an AWS AMI data structure that looks for the right AMI image that is owned by our owner ID. This is the Varnish Software Marketplace image. And we'll use that to spin up a Varnish Enterprise instance. It uses the instance information that comes from that data structure, it also uses my key, and it leverages the S3 shield YAML file to orchestrate that. There's a bunch of tags, project and name, and then when we go to variables, we need to tune that. So we'll deploy it, where it first says US West 2, we're going to deploy it to US West 3, which is Paris, use the T2 micro instance, and use my personal SSH key. With the Terraform files in place and the variables configured, we can go back to the command line and actually run the Terraform command to spin up that EC2 instance using the cloud-init automation scripts. We're still in the S3 Shield folder and we can navigate to Terraform AWS. The file list shows all the relevant files and we need to regenerate the cloud-init file. Then we can run Terraform init that loads all the dependencies, including the AWS plugin for Terraform. And after that, we can run Terraform plan to run a dry run. This gives us a pretty decent overview of what's about to happen and what resources will be provisioned on Amazon, ranging from security groups to the instance itself. And then finally, we can run Terraform apply, and that plan will now be executed. We just type yes, we confirm, and now the creation happens, which could take a little bit of time. Creation is complete and the output lists both the private IP as well as the public IP. So we can now take the public IP and do our typical run. And our typical run consists of a curl command that we run both on the S3 bucket itself, and then we compare it to the results coming from our freshly created Amazon machine hosted in Paris. And as you can see, the results are good. You can transition from a more traditional cloud deployment, if you will, by using EC2 instances into doing it more in a cloud native way and run Docker images, either standalone or orchestrated in Kubernetes. Let's start with the standalone bit and show you how you can orchestrate it using a Docker Compose file. Let me take you back to the editor and you'll see a Docker Compose folder in which you find all the necessary files. As always, there's an s3.conf file. You put your bucket address in it, your access key, and your secret key. You can optionally tune the TTL, and that file will be loaded by the docker compose.yaml file, which is the orchestration file that mentions which container to create, using what image, and all the other bells and whistles. So if I take you there, you'll notice that it uses the custom image provided by us by Varnish software called Varnish Plus. This requires a token to access it, which is part of your Varnish Enterprise subscription. In the next step, we'll load the necessary files. So of course, there is the custom VCL file with all the S3 logic in it that lives in the parent folder. And then of course, we'll load the s3.conf file. These files are also referenced as environment variables and used inside the container. And then finally, there's some port forwarding taking place in this orchestration file, forwarding port 6081 of Varnish to port 6081 on your local computer. So if you run this on your local system, it will port forward it to 6081, and that's how you can access it. So let's try that out. We can now go back to our command line, navigate to the Docker Compose folder, and list the files. You can see that the Docker Compose YAML file is there and the s3.conf file. And then it's just a matter of running the Docker Compose up command, and it will bootstrap everything. As you can see, it runs the Varnish Enterprise deployment, has all the bells and whistles in it. And if we do a split screen, we can run the curl command again to see what is going on. So as always, we start off by loading the S3 bucket itself. 370 milliseconds is the time. We replace it. In this case, this runs locally with localhost port 6081. And as you'd expect, it's slow the first time, 464 milliseconds, but now it's in the cache. And when you run it again, it takes 2 milliseconds. That's pretty damn great, 5 milliseconds. So that is some excellent performance right there. But of course, it runs on the local computer. There's zero network latency. And if you want to see it for real, just go to your browser, type localhost:6081/logo.jpg, and you'll see the cached version of that logo hosted locally on your Docker setup. But let's be honest, a lot of people orchestrate Docker containers in a Kubernetes cluster rather than doing it using Docker Compose. And the orchestration layer is often done using Helm charts, which makes the creation of the definitions of Kubernetes resources a lot easier. Of course, we have an official Varnish Enterprise Helm chart, and we have some customizations in place to orchestrate an S3 shield. Let me show you how that's done. Let's head back to the editor, open up the Helm folder and look at the files. It comes as no surprise that there is an s3.conf file. You know what to do with it by now. You open it up, change the bucket address. In our case, that's setting it to Varnish-example in US East 1. You alter the access key and the secret key, and that will be used later on. The Helm chart has a set of templates and a set of default values for variables which you can override in the values.yaml file. The values.yaml file starts off with an image pull secret. It's called varnish-pull-secret, and it contains your personal credentials to access our private repository for the Varnish Enterprise Docker image. It's part of your subscription and we expect it to be there. Our documentation website explains how to exactly create that and what command you need. Continuing on with the values.yaml file, another override we do is setting extra environment variables, AWS shared credentials file, AWS config file. These point to etc varnish aws s3.conf. These files are typically not there in the Varnish Enterprise container, so we need to mount them in there. Hence the extra volumes definition. Those refer to config maps and secrets. And we'll create those config maps and those secrets separately using specific kubectl commands. So here's the command you need to mount the default VCL file as a config map. And here's the other one you need to mount the s3conf file as a secret. So if you do helm list, there's nothing yet deployed, and then we can do helm install and use the values.yaml file to load a deployment called Varnish Enterprise. You can see that it's now listed. And if we do kubectl get all, we see all the elements that were deployed. So the pod is there, and there's also a service present that does a port forwarding of the Varnish Enterprise container from port 80 to port 30134. So now we can do that curl call again and call our S3 bucket with, of course, a slow response time. Now we can use that port and go to localhost, because I'm running this Kubernetes cluster locally, and use that forwarded port 30134. First one is rather slow, 461 milliseconds, but doing it again, it's lightning fast, 3 milliseconds. And that's how our Helm chart works. You can deploy this, of course, locally on your local Kubernetes cluster, but eventually you can run this in a Kubernetes cluster in the cloud and orchestrate it there. And that's the last piece of the puzzle. Thank you for watching this video. I hope you understand what an S3 shield is and you appreciate the value it brings. I also hope I convinced you that Varnish Enterprise is a very valid candidate, and that the different automation steps that we offer suit your needs. We covered Ansible, we covered cloud-init on more private environments or in one of the big hyperscaler clouds. We talked about orchestrating it via Terraform, we talked about Docker, we talked about Helm. If you're interested in knowing more or getting started, well, reach out to us. You can do that via our website. There's a chat widget on the website, and the website itself also contains information about our product. You can also press the blue Talk to an Expert button in the navigation. This takes you to a form where you can leave your contact details and ask some questions, allowing us to get back to you via email. So thank you for watching this video, and I'll see you next time for yet another video.